Okay, if we have an ellipse, x squared over 16 plus y squared over 9 equals 1. A squared is 16, so A is 4, the length of the semi-major axis. B squared is 9, so B is 3, the semi-minor axis. This gives us an ellipse, okay? Semi-major axis 4, semi-minor axis 3. It looks like a football, slightly deflated to 10 pounds per square inch, so Brady can get a grip on it, all right? If we had the ellipse defined differently, and today is the 15th, I think. Okay? If we had a different ellipse, slightly different, like so, x squared over 9 and the y squared over 16 equals 1. The a is still the greater. This is now going to be a squared. A is still 4. Okay, a is the greater, but it's along the y-axis now. So what you have is this. This is 4. That's the semi-major. The semi-minor is 3. And you have this ellipse like so. Okay? That's the difference.
Okay, so in this case, then they're just switched?
Yes.
Okay.
Yes. Okay, any other questions on homework? Yes, question?
Well, not so much on the homework, but
Oh.
if the greater one is always going to be A, then
Yes.
what's the significance of it actually being A?
What?
So, like, the biggest one's always going to be A, right?
In an ellipse, A is always the greater of the two, yes.
Right. But even though the axis is still going to be different depending on which one's the bigger one.
Yes, yes.
So what's the significance of it actually being A?
Well, because when you have to find the foci, here and here, okay, it's the fact that b squared plus c squared is equal to a squared. And so the a has to be the greater of the two in order for that to work. That's what you need. Okay. Yes?
Could you actually write out like a verbal definition of the foci and the directrix?
Oh, God.
Because like I was looking at that and I was kind of struggling like what they actually represent.
Well, okay. Oh, okay, if you talk about directors, you're talking about parabola.
Yeah.
Okay.
And this goes back a ways.
This goes back. Here, let me do that. A parabola. Let's just go back here. The original definition of a parabola is the set of points in a plane, okay, equidistant between a given point, the focus, and a line, the directrix. So what is a parabola? It's a set of all points in the plane equidistant between this focus and the line. Now, the first point that qualifies would be this point right between the two, and that point is the vertex. Okay? And as you move away from the origin along the x-axis, what happens is that those points that satisfy those conditions would move up this way, because you need this distance equal to this distance. Okay? Those two distances have to be the same. And it's the same on the other side. Okay? Same thing would have to occur, where this distance is equal to this distance here. Okay. So, what is the focus? It's the original point in the definition of a parabola. The directrix is that line. Okay. The equation for the parabola that you get, in general, if you move this off the origin, is x minus h squared 4p y minus k. Okay. HK give you the vertex. P is important. It's the distance from the vertex to the focus. It's also that distance from the vertex to the directrix.
Yeah.
Oh.
I just don't know how you rattle this stuff off like that.
Well,
36 years.
yeah. Okay. Okay, what do you think?
So as that point in the right-hand corner moves further away from the origin,
It moves up.
directrix will move downward.
Directrix does not move.
Oh, I see.
The directrix stays the same, focus stays the same. But what I'm saying is the set of points that are equidistant between this and this, as you move this way, that set of points moves this way. Yeah, that's what happens. Okay, what do you think, Dave? Is that okay? Any other questions at all? Yes, Omar.
One more similar to this.
Simply.
I was working on WebAssign and I tried using the standard form to solve a problem.
Yes, you did. Good man.
And it came out wrong the first time when I used standard form, and so I switched some values around and it came out correct. But I'm not exactly sure what I did.
Wow.
They were asking.
And you're asking me if I have a hidden camera in your room and I saw what you did?
Well, I have the work I did, so I thought you might look at it.
Oh, I'll tell you what, I'll look at it right after class.
Okay, sure.
How's that? Is that okay?
Yeah, that worked.
Yeah, okay. All right, I'll take a look. Any other questions? Okay, let's go on a little bit. Yeah, I'll take a look at that. And by the way, Nick, who's not here, is getting these videos up at YouTube. If you go to YouTube right now and type in I don't know if the Burns comes first or what. Burns Calculus 3 in YouTube. Okay? You'll get these videos of Calc 1, Calc 2, and the Calc 3 videos that he's done so far. Check it out. Check it out. Make sure. I think it's Burns Calculus 3. It could be Calculus 3 Burns. You got him?
Your hands all over the place.
Yeah. So, that means, that's really good news. Because what it means,
No views? One view? Get some views on there.
well, he just did it. He just got him up there.
Come on, man. You gotta be faster than that.
11 hours ago?
Ooh, there's some guy from Princeton there too.
What?
Uh-oh. Competition.
All right, what it means though, this is we're going to get these up there, and if I can remember to record, which, as we saw today, it's pretty doubtful, but if I can manage to do that, we're going to get these up. So that means what? If you miss a class, the videos are there. Okay, not only do I have the notes, but you'll see what I did.
He's doing a hand model. No. About 3 views. She's like the guy from the One view. I'll be the second one.
Anyhow, it is good news if you do have to miss a class. Okay, so keep that in mind. All right. Okay. Are we ready? Let's go on. Let's go on and do some polar coordinates. It turns out that our rectangular coordinate system is really not sufficient to do all the graphs that we want to do. Okay? We need another coordinate system. Actually, by the end of the course, we'll need a third coordinate system, a spherical coordinate system as well, to do things with triple integrals especially, that deal with spheres, okay? Specifically with spheres. But right now, in 2-space, we're going to need what is called a polar coordinate system. Let's take a look at this. Okay. In a polar coordinate system, we have 2 axes. But this is called a polar axis. And this axis is theta equals pi over 2. And this line segment going this way would be theta equals pi. This would be theta equals 3 pi over 2. This would be theta equals 0 as well. Okay? Instead of being called the origin, where the 2 axes intersect, this is called the pole. Okay? Santa lives here. No, this is, I can't resist. We locate a point in the plane with 2 real numbers. These real numbers are r and theta. Okay? R represents the distance, the directed distance from the pole, and theta is the angle this directed line segment makes with the polar axis. Okay? Now, one thing you're going to have to be able to do is take from polar coordinates and change to rectangular, and from rectangular back to polar coordinates. So let's do that right now. This is the x, this is the y. Let's do x and y first. What's x equal to in terms of r's and thetas? Thank you. It's r cosine theta. Just solve the right triangle here, okay? And what's y equal to? R sine theta. Very nice. Thank you very much. So if we know r and theta, we can change it back to rectangular x and y, and we're going to have to do that on occasion, okay? Also on occasion, we're going to have to go the other way. Given x's and y's, we'll have to go to r's and thetas. So what's r equal to in terms of x's and y's? Perfect. Square root of x squared plus y squared. Now, it is a directed distance. It is possible that r could be negative, okay? It's possible. I'm going to put a plus or minus here because it's possible that to have r negative. Generally speaking, if we have two ways to express a point, and I'll tell you, in polar coordinates, there are an infinite number of ways to specify this point. An infinite number of ways. We'll do one of those in a second, okay? But generally, if you have a choice between r positive or negative, you choose r positive, okay? And what's theta equal to?
X over Y, tangent of X over Y.
Yeah, it's the inverse tangent. Yeah, you got it. That was good. That was good. That was it. Inverse tangent, arctangent, y over x, okay? So let's take an example. For example, let's locate a point. Let's say our point in polar coordinates is pi over 6. Is equal to 5 and then pi over 6. R and then theta. Okay? Let's find the x and y. What's x equal to here? R cosine. That would be equal to 5 cosine pi over 6. Cosine square root of 3 over 2. And y would equal 5 sine of pi over 6, 1/2, 5 halves. Yep. And that would be its x and y in a rectangular coordinate system. To go back the other way, however, okay, sometimes it's a little tricky. Let's do another problem. Let's take a point in rectangular coordinates. Let's take, let's take 1, 2 in rectangular. Okay, and let's change it to polar. And in polar coordinates, we need an r and a theta. What's r equal to? Square root of 5. And what's theta equal to? Who knows? It's the inverse tangent of y over x2. It's the inverse tangent of 2. That's one way to describe that point, though, in polar. We have other ways. Okay? Can someone give me another way of describing where that point is in polar coordinates? This would be the best way. It would be square root of 5, inverse tangent 2, arctan 2. Okay? What would be another way to describe that point in polar coordinates? Bless you.
Cosine and sine.
Well, no, I mean, like, using tangents and square root of 5, there are other ways to describe that point.
At 360 degrees.
What's that?
At 360 degrees.
Add 2 pi radians to it, 360 degrees. Sure, that works. That would be another way to reference that point. or subtract 2 pi, or subtract 2k pi, where k is any integer at all. That would give you an infinite number of representations of that point. But yet there are other ways of doing this. Watch this. If you were to go this direction and say this is a distance of square root of 5, we could still get back here by using a negative square root of 5 as our distance with this angle. Okay, what angle would this be? This would be an angle of,
I plus
you,
inverse tan.
exactly right, pi plus that, add 180 to this to get over to here. So here's another way of referencing that point. Do a negative square root of 5 pi plus inverse tangent 2. Believe it or not, that would get you to the same point 1, 2 from before. Okay? Do the angle. The angle would get you to 180 degrees from here along that line, and a negative square root of 5 for r brings it through the origin out to the other side. It reverses its direction. So keep that in mind, okay? That would be a possibility. I think in WebAssign they ask you to do something like that, okay? All right, what we'd really like to do, though, most of the time is, once we're in polar coordinates, stay in polar coordinates. There are certain functions in polar coordinates that we're going to use, that we're going to need polar coordinates to graph. They're easier to deal with in polar coordinates. Let's do some of the common polar coordinate functions here. Let's start with, generally speaking, in polar coordinates, you have r is a function of theta. Let's start with the simplest possible. Let's start with r equals some constant. Let's say r equals 2. Oh, jeez. I'm going to do that automatically. That's a muscle memory thing. As soon as I draw axes, I'm going to draw an x there. But I'm in polar coordinates now, okay? Polar coordinates. Okay. What is the graph in polar of r equals 2? What set of points satisfy the condition that r equals 2 in a polar graph?
Circle with radius 2.
Perfect. Perfect. That's exactly right. Okay? This would be 2, 0. This would be 2 pi over 2, 2 pi, and 2, 3 pi over 2. Okay? That describes that circle. Now, this is the reason that polar coordinates are going to be valuable. If we're dealing with circles in a plane, its polar equation is r equals 2, a constant. Its rectangular coordinate system representation is x squared plus y squared is equal to 2, square root of 2. Okay, no, 2. 4. Let's go to 4. X squared plus y squared equals 4. Much more complicated representation of this circle. Okay? When we go to 3 dimensions, and we're talking about centers of mass of solids in space with varying density, which we're going to do, and talk about spheres, the equation of that sphere is rho equals 2. That's the equation of a sphere in space and spherical coordinates. That's why it's much easier to work with spherical coordinates with spheres in space, because the very definition of a sphere is a constant. The very definition of this circle here in polar coordinates is a constant, r equals 2, which is going to be easier to deal with when we have to deal with this, okay? We're going to have to find volumes underneath surfaces over regions in the plane. If that's a region that's a circular region, we're going to use polar coordinates to do that problem. It's going to be much easier that way, okay? So that would be a very simple polar equation, r equals 2, which is a constant. Let's do another one. Let's take theta equals a constant. Okay, how about theta equals pi over 4? What would that be? Oh, for Pete's sake, I knew it. I'm going to do that all the time. What set of points in this polar system would satisfy the condition that theta equals pi over 4. Straight line. Who said that? Straight line, good. What's the slope of this line? 1. Yeah, this would be a constant pi over 4 angle here. Every point on this line has a theta equals pi over 4. That's the angle it makes with the polar axis, okay? All right, so there's two common, simple polar equations. Let's crank it up a little bit so it get a little bit more complicated. Let's go with r equals theta. Jeez. Okay, r equals theta. What do we get for a set of points here where r is equal to theta? Start at the origin. Go ahead.
Like a spiral?
You bet it does. If we keep r positive, here's what happens. You start here. As you increase theta, r will increase. Okay, what happens is you come around this way. As you keep on increasing, you get a spiral. And if you allow r to be negative as well, what happens is, as you start here, you end up with, okay, what's that?
Isn't there a name for that? The spiral?
Yeah, it's an Archimedean spiral. That's exactly what it is. It's an Archimedean spiral. One of the many, many things that Archimedes came up with. Archimedes is just flat out genius, okay? Just awesome.
Pretty good, man. Could have made YouTube videos. It would have been big.
He would have gone viral. He would have gone viral. Yeah, he would have done it. Okay, if you allow r to be negative or theta to be negative here, if you start here and do negative values of angles, what happens is you get the other side of this thing. You can get this, if I can do this right here. Okay, hold on a second. As r increases, theta increases. Yeah, okay. As r increases now, theta will decrease. So we're going to get, instead of going out this way, take another value. Okay, I think I'm going to get this. Something like this. All right. Something like this on the other side. Okay. I don't know. You can do this in Mathematica, by the way, with a polar plot. And matter of fact, we're going to look at that on Thursday because your first lab is a polar plot. Okay? We're going to do some polar plots. Let's take a look at something more useful than that. We're not going to use Archimedean spirals here. Okay? Let's do r equals cosine theta. Let's take, see that? I've learned. Okay. Let me come up with this one. R equals cosine theta. What the heck we got?
Cosine?
No, you don't. No. One would think, but you don't.
Right, like in a circle.
Yes, you do get a circle. That's exactly right. Watch this. Start here at theta equals 0. As you increase, when theta is equal to 0, r is equal to 1, actually. It starts here. Okay? Now, as you increase theta, what happens to r? It decreases. Cosine decreases. Okay? At pi over 2, cosine of pi over 2 is 0, r is 0. We're at the pole at pi over 2. As you continue increasing theta, come over here into the second quadrant here. What happens to cosine? It goes negative. Okay, so the r comes back over to the other side. It continues this way. At pi, when theta is equal to pi, the cosine of pi is equal to -1. We're here. We're back here. Another name for this point is -1 pi. Okay? When theta is pi, the cosine of pi is -1, r is -1. So here's pi. Out here, r is -1. Go back through the pole, out the other side 1 unit. And you repeat the process, okay? This is a circle that completes the circle in pi radians. And you got to be careful when doing areas and polar coordinates. We're going to do that probably tomorrow when we finish this up. Okay? When you do this area, it looks like you should integrate from 0 to 2 pi. But no, that's wrong, because that'll go around the circle twice. Okay? So you got to be careful with something like that. What kind of symmetry do we have here, by the way? What kind of symmetry does this graph have?
X-axis?
What's that?
About the x-axis?
Yeah, what used to be the x-axis, which is now the polar axis. You got polar axis symmetry. And that's typical of polar functions involving cosine. And why is that? Because cosine is what kind of a function? What is it?
Odd. Even.
Even. Good deal. Cosine is even, which means what? Even functions, cosine of the opposite of theta is the cosine of theta. That's characteristic of even functions. Replacing the argument x or theta with the opposite gives you the same thing back again. Y equals x squared, even function. Symmetry with the y-axis. In rectangular coordinates, even functions have symmetry with respect to the y-axis. Replacing x with its opposite causes no change. Okay? In polar coordinates, even functions have symmetry with respect to the polar axis. Think about it. If you replace theta with its opposite, it's no change. Here's theta. You get this r. Well, opposite of theta, you're going to get the same r. The same r. So what happens is, this is bisected by the polar axis. That's what polar axis symmetry means. That line segment is bisected by the polar axis. And that's true of that's characteristic of even functions in a polar system, which is cosine. Okay? Now, could we take this circle in polar coordinates and change it to rectangular coordinates? Could we do such a thing? Of course we could. Dylan, we can do anything. So let's do it. But there's a trick here that I should point out to you. Okay. Here's what you could do. What you could do is replace r with the square root of x squared plus y squared, and replace theta with the inverse tangent of y over x. That's what you could do. That's r. And that's theta. And you've eliminated the r's and the thetas, and now you're in terms of x's and y's in rectangular coordinates. You could do that, but that is really nasty, okay? You could handle this. How would you handle this? What would you do with this expression to do something with this? What would you do?
Right triangle.
Right triangle is correct. Matter of fact, I'm going to do it, and then I'll show you the better way. But I'm going to show you this way first. Then you'll appreciate the better way more. Let's do this. You do this with a right triangle. You call this angle inverse tangent y over x, because the inverse tangent of y over x is an angle. That's what inverse trig functions are, angles. Okay. What's the tangent of this angle? It's the ratio of the opposite over the adjacent side. But what is the tangent of the inverse tangent of y over x? Y over x, because a composition of a function with its inverse gives you the original argument y over x back again. So the tangent of this angle is the opposite over the adjacent. And the tangent of this angle is y over x. So what do? You make it y over x so that you get the right ratio that we need there. Okay, is everybody okay with that? People are dying on me. How much time we got? All right. What's the hypotenuse then? Square root of x squared plus y squared. Okay. Okay, so what do we need here? We need the cosine of this angle. What's the cosine of this angle?
X over square root of x.
X over the square root of x squared plus y squared. Adjacent over hypotenuse. Well, this isn't too bad. Multiply both sides by the square root. You get x squared plus y squared equals x. Not too bad. Set it equal to 0. Move this x over. Complete the square. What do you do to complete the square here? Who said that? Add 1/4 to each side. Okay. We okay? We have x minus 1/2 squared plus y squared equals 1/4. Obviously, we have a circle whose center is 1/2, 0, and whose radius is 1/2. And guess what? How you doing? When we did it in polar coordinates, what did we get? We got this circle whose diameter here is 1, whose radius is 1/2, and whose center is 1/2, 0, and a rectangular coordinate system, which is exactly what we have here. Okay? That's the long way. You can do it that way, but there's a trick to doing it. What's wrong? What do you need? Oh, okay. The trick is to go back to the original. Okay? And the trick is to multiply both sides by r. Okay? Why? Well, you want r cosines rather than cosines. Because what's r cosine equal to? X. Okay? And you want r squares rather than r's because now you don't have a square root anymore. Okay? It's two advantages there by multiplying both sides by r. R squared is x squared plus y squared, and r cosine is x. Okay? So we end up down here at this point without having to go through this, or this, and this. Okay? So it's a better thing. It's a better way to do it. It's take advantage of that relationship. Now bring the x over, and obviously you get the same thing you had before. Okay? How are we doing? Okay? So let's do another one of those. So let's do r equals sine theta. You guys do it. Figure it out. You guys can figure it out. What does r equals sine theta look like? You guys can figure it out. I can't move this chair. Okay. Who's going to answer? He is confident in? Yes.
Same thing, but along the y-axis.
It's perfect. Good job. Okay? We get a circle. Now it's along the y-axis, or theta equals pi over 2. And if you trace it out, you start at 0, sine of 0 is 0, r is 0 here. As the theta increases, sine increases. When you get to pi over 2, the sine of pi over 2 is 1, r would equal 1. So it comes around this way, here. Now, as we get into the second quadrant, sine is positive, okay? Sine continues positive, but now it's decreasing from 1 back to 0 again. So it's going like this. Okay? So this point right here would be 1 pi over 2. This point right here is either 0, 0 or 0 pi. Okay? This point here. As you continue increasing theta, now we're in the third quadrant where the sign is negative. Okay? And what happens is the r will be negative. So you get these angles coming out here in the third quadrant, but the negative value brings it over back into here into the first quadrant. So you repeat the circle. And you go around, you trace it around twice, just like you do with cosine. What kind of symmetry do we have with sine? Theta equals pi over 2, y-axis symmetry. Typical of odd functions in polar coordinates. Why is that? What's characteristic of odd functions? Well, the sine, this is an odd function. If you replace theta with its opposite, you get the opposite of the original. That's characteristic of odd functions. Okay? Y equals x cubed. Odd function. Replace x with its opposite, and you get the opposite of the original. You get a negative x cubed. Okay? In rectangular coordinates, what kind of symmetry do we have with odd functions? About the origin is correct. Okay? We get origin symmetry. Take a point, draw a line through the origin to the graph. The origin bisects that line segment. Okay? In polar coordinates, those odd functions give us symmetry with respect to theta equals pi over 2, the y-axis. And does that make sense? Here, let's take, here's theta, some theta and some r. You get this. Okay? Now, I'm going to replace theta with its opposite. Instead of this, I'll get this. But I get the opposite of the sine. I get the opposite of this distance. I get a negative value for r, which takes it from here and moves it this way. The same distance. Okay? Guess what? We get a point here. This would be the point, negative theta, opposite of theta, and a negative r. And it's bisected by theta equals pi over 2, giving us the symmetry we know we have. Okay? So replacing theta with its opposite brings you here, and we get the opposite of r, the original function, brings it up here, and we get that symmetry. Okay? One other thing you should realize here with these, you've got tangents, two kinds of tangents to these things. Tangents at the pole. We'll take a look at this tomorrow some more too. Okay? Oh yeah. Good call. Tangent at the pole. This one here, the x-axis itself, the polar axis, is the tangent to this graph at the pole. You get tangents to polar graphs at those theta values where r equals 0. Okay? So when r is equal to 0, that theta is the tangent at the pole. We said theta equals a constant, is a line through the origin. We did that a little while ago. This one here, what makes r equal 0 is to have theta equals 0 or theta equals pi, and that gives you a tangent to the graph at the pole. When we did cosine, okay, what causes the r to be 0 here? Pi over 2. That gives us our tangent to the graph at the pole. Okay? Whatever causes r to be equal to 0, that theta is a tangent line to the graph at the pole. Okay? But there's one other thing, and that's the actual tangent line to the graph, this tangent line, which we are going to need sometime. And if we're going to have a tangent line, guess what we need? We need dy dx, okay? That's the slope of a tangent line no matter what the coordinate system is. It's still dy dx, okay? So here's the deal. Let's take r equals sine theta. Okay, is everybody okay? All right. Is everybody okay still?
Still breathing.
What's that?
Still breathing.
All right, well, that's okay then. For a lot of you guys, that's probably a plus. It's probably a good day. All right. Jeez. Okay. Here's r equals sine theta. Okay. And let's suppose what we want to do is find the slope of the tangent line at something, pi over 4, say, or pi, yeah, let's do pi over 4, what the heck. And what we want is the slope of the tangent line at that point. Now, right now, it looks like it should be something like this, like -1 maybe or something. It's possible, though, that if I were to draw this, right, we get a slope that's undefined here. So the question is, how do we find this slope of the tangent line? There are two ways. One way to do this is to say, let's go to rectangular coordinates. Let's convert it from r equals sine theta. Let's go back to what we discovered we could do, change it to rectangular, multiply by r, replace it, and get that x minus 1/2 squared plus y squared equals 1/2 thing, okay? Or in this case, it would be on the y's, and find dy dx that way, use implicit differentiation. It's kind of a pain. But there is another way. It's not all that much better, though, unfortunately. The better way is to change this to parametric form, okay? You change this to parametric form by doing the following. And we're going to have to do this a few times. And this is the last thing I'll do today here. Change to parametric form. We know that x is equal to r cosine theta. And we know that y is equal to r sine theta. Okay? We are given an equation where r is equal to sine theta. Here's what we're going to do. We're going to take the r equals sine theta and replace this r with sine theta. We're going to say x is equal to sine theta cosine theta. Y is equal to sine theta, sine squared theta. Okay? This is a polar equation. This is a parametric form. The rectangular form we already know about. That's the completing the square thing. Okay? Let's find dy dx using the parametric form. We can find dy dx by taking dy d theta and dx d theta using the chain rule. Okay? You guys still okay? Dylan, you okay?
How did you derive x and y for the parametric forms again?
Right here?
Yeah.
I replace this r with sine theta, and I replace this r with sine theta. So here we go. Okay? Polar form, parametric form, and then there's rectangular form. Okay? It's interesting, in Mathematica, you plot them the three different ways. There's a parametric plot, there's a polar plot, and there's plot for the rectangular. And all three of them will give you the same graph, obviously, and three different things. But dy d theta, let's take the derivative of sine squared, which is 2 sine theta cosine theta. Okay. Let's take dx d theta, take the derivative, product rule first, derivative of the second, plus second times the derivative of the first we end up with 2 sine theta cosine theta. I'm going to write the cosine squared first here, minus the sine squared. It's kind of interesting, but what's 2 sine theta cosine theta equal to? What? Sine 2 theta, trig identity, double angle. And what's cosine squared minus sine squared equal to? No, that would be a negative cosine squared minus sine squared. Yeah, you have to get multiplied by -1. What is it?
2 cosine squared minus 1.
Yeah, it is 2 cosine squared minus 1. That's not what I want, though. That is true, though, but it's not what I want. Cosine squared minus sine squared is? Cosine 2 theta. Oh, is it up there? They have the double angles? Oh, there it is. Cosine 2 theta, cosine squared minus sine squared. There it is, right there.
Will those be up for the exam?
Yeah. I'm not going to erase it. It says do not erase. All right. So that's and actually, what's sine 2 theta over cosine 2 theta equal to? Tangent 2 theta. That's pretty cool. Okay, so here's what that's what I thought. Look at that. Wow. Theta equals pi over 4. What's the slope of the tangent line? That slope of the tangent line, dy dx, that derivative is equal to the tangent of 2 times pi over 4, which is the tangent of pi over 2, which is tangent of pi over 2? What is it? Undefined. So, if I had drawn this, I was concerned about that. You know that? The actual pi over 4 comes over here, a little bit off, but the slope of the tangent line is this. Okay? It's undefined.
Oh well. Next time.
Next, thank you. You're being very generous, Ted. All right. Yeah, I think that's a start to the polar coordinates. We're going to do some polar graphs, some more polar graphs tomorrow. We'll do some limicons, some cardioids. We'll do some roses, some good stuff. And we'll finish up tomorrow with the polar coordinates. What's that? Oh, we're all set. See you. Now.
In 30 minutes.